There are different types of organic reactions, and each one of these reactions we will consider in a separated chapter. The first one is the substitution reaction, which we will discuss in this chapter. So, with substitution reactions, you start with your reactant, and your reactant normally has a heteroatom on it or a hydrogen. If Z is a hydrogen, then you will be working with an acid base reaction. The idea here is that you're replacing the Z with your reagent. Y is your reagent, and you simply switch Z with Y. Now, Y is going to be your nucleophile, and the nucleophile always needs to have electrons in there. So this is going to be a nucleophile, and the reaction is going to be the nucleophile is going to come and attack this carbon over here, break the bond, and Z is going to leave. So it's a simple substitution where Y replaces Z. So this is your Y in there, and the Y is going to replace the Z, and Z now is going to be your leaving group. So this is going to be the leaving group. Okay, let's have an example in here. Remember what we said every single time when you do organic reactions, you would need to have a species that is electron deficient and another one that is electron rich. So the nucleophile here is going to be your chlorine. Chlorine is electron rich, so this is going to be your nucleophile. And because iodine is an electronegative element, the iodine is going to pull electrons away from the carbon and make it partial positive. So in this case, your electrophile is going to be that carbon. So this carbon here is going to be the electrophile. The reaction always happens between the nucleophile and the electrophile. And the arrow is going to be as such. The nucleophile is going to come, is going to attack the carbon in there. And every time you make a bond, you're using the lone pairs of the chlorine to make a bond with this carbon. You have to break a bond so that to make sure that you follow the octet rule of the carbon, because if iodine still is there, then the carbon will have 5 bonds. So every time you make a bond, you have to break a bond, and iodine now is going to be your leaving the group, and your product is going to be the alkyl group that has the halogen on it. This halogen was once a nucleophile, and the nucleophile replaced the iodine. This is the same idea over here. So pick your electrophile from your reactant. So over here, I do have my partial positive carbon because the oxygen and the chlorine, they both take electrons from that carbon, making it partial positive. So now this carbon is going to be my electrophile, and the nucleophile is going to be the OH. Again, the nucleophile needs to have electrons. So anything that has electrons is considered to be the nucleophile. So now my reaction is going to be from the nucleophile to the electrophile. So from the OH towards the carbon in there. And every time I make a bond, I need to break the bond. The bond that I am breaking here is the bond between the carbon and the halogen. This is the bond that I am breaking, this one over here. So you break this bond, and when you break this bond, it's as if you did a substitution here of the chlorine by the OH. So you're going to end up getting your product here, and whatever left, this is going to be called the leaving group. Another type of organic reaction that we will discuss in the next chapter, this is elimination reaction. In elimination reaction, I need to break my 2 sigma bonds and I need to form a pi bond. This reaction happens whenever I have heat in my reaction conditions. So substitution does not require any heat. The reaction simply happens when the nucleophile attacks the electrophilic carbon. However, you would need something that leaves in there. Z needs to be either a heteroatom or a hydrogen. On the other end, with elimination, you need to have heat. And with heat, you are breaking two sigma bonds. The sigma bonds that you are breaking are the bonds between the carbons and X and Y. So carbon X, this is the first sigma bond that you're going to break, and carbon Y, this is the second sigma bond that you are going to break. Your reagent here that you are using needs to be a base. So this one needs to be a base. And most of the bases have lone pairs, or all of the bases, they have lone pairs. So it's similar to a nucleophile in there. So in this case, the base is going to come. It's going to take the hydrogen, form a double bond, and the halogen is going to leave. So you are going to end up getting your product that is an alkene. With elimination, your product is always an alkene. So here, this is going to be my product, and the product is always going to be an alkene. And what's going to happen here is that the base is going to come, it's going to take the hydrogen, it's going to form a double bond, and the halogen is going to leave. So what I'm doing over here is that I'm breaking this sigma bond, and I am breaking this sigma bond in there. And every time you break two sigma bonds, you have to form a pi bond. So the bond here that I am forming is a pi bond. So every time you look at a reaction and you see that your product is an alkene, then this is going to be an elimination reaction. And as we said, an elimination reaction is the breaking of two sigma bonds and forming of a pi bond. This is another example here. So if I'm going from this reactant to this product, I know that my product has a double bond. So immediately this is an elimination reaction. What did I lose? I actually lost an OH. This is going to be my first sigma bond that I lost over here. So I lost my OH, and I lost the hydrogen that is connected to the oxygen. So here, this is what I lost. So let's make it like that over here. And I lost, this is my second sigma bond in there. So I lost my two sigma bonds. I lost the sigma bond here, and I lost the sigma bond in there. So I'm going to go ahead and form a double bond between the carbon and the oxygen. So here in reality, I lost water. So water is going to be my leaving group. I can write also this reaction in another way, where I'm starting also with a dialcohol. This is a 2-alcohol in here, same reactant. If I want to do elimination here, I can lose, for example, the sigma bond between the carbon and the OH. Instead now of losing this hydrogen here, I can go ahead and lose this hydrogen over there. So I can lose this hydrogen over here. These are still two sigma bonds. This is a sigma bond here, and this is a sigma bond there. Always the double bond is between the two carbons that carry the sigma bond. It will be between those two carbons, and my product is going to be a double bond over here, but I still have one OH, so you simply keep that OH. And this is another elimination product for that same reactant. A third type of reaction is the addition reaction. Addition means that this is the opposite of elimination. Addition is whenever you start with an alkane and then you add a reagent that has two components to the alkene. So you break the pi bond and you form two sigma bonds. This is called an addition reaction. Notice that your product does not have an alkene anymore, but what you did is you broke the pi bond and you formed your two new sigma bonds in there. Let's have an example, starting with an alkene. You are adding to the alkene, so one of the components of the reagent will go to one carbon, and the other component of the reagent will go to the second carbon, and you're going to end up having your product in this case. Now, this example includes a symmetrical alkene. Sometimes the alkene is not symmetrical, so we're going to discuss that whenever we reach the chapter for this reaction. Same thing over there. If you have a carbon double bond O and you react this with hydrogen in there, this is called an addition reaction. Hydrogen H2 is basically two hydrogens that are connected together by a covalent bond. So I'm going to break the pi bond, and I'm going to add one hydrogen to this carbon, and I'm going to add one hydrogen to this oxygen. So I'm going to end up having my alcohol as a product. Inorganic reaction mechanism is important. And the reason why it's important because you show how bonds are broken and how bonds are formed. This is completely different than writing the product of the reaction. When you write the product of the reaction, you don't show how bonds are broken and how bonds are formed. But when you're asked to write the mechanism reaction, then you would need to show arrows. You would need to show the flow of electrons and how you are breaking your bond and how you are forming the bond. Reaction mechanisms can happen either by one step or by multiple steps. The one step, we call it a concerted reaction, where you simply go from your reactant to your product. However, if you have multiple steps, we call this a stepwise reaction. You start with your reactant and then you reach an intermediate. And then from the intermediate, you form your product. Or you can form another intermediate and then do a third step until you go ahead and you form your final product. Two types. There are two types of how bonds break in organic reactions. Bonds can break either by a homolytic cleavage, and the cleavage always involves the sigma bond. So you are breaking the sigma bond. So this is the sigma bond that you are breaking. And we know that every bond is made up of two electrons in there. Okay. So the first type of breaking of the bond is whenever you break the bond in half and every atom in the reactants take just one electron. This is called a homolytic cleavage, where the sigma bonds they are broken equal by equally dividing the electrons in there. So what you're going to form here is products that are called free radicals. It's a free radical because it has one electron in there. So each one of these components that make up the reactants, those will end up having just carrying one electron. So they won't be octet. The product here is not going to be stable in this case. Another type of reaction is the heterolytic cleavage. The heterolytic cleavage is when one atom in the reactants takes all the electrons. So here the sigma bond has two electrons in there. And as my arrow is showing that the B is taking all the electrons. So when this happens, then A will be electron deficient. And I need to represent that. So to represent that, if A is a carbon, then we're going to call this a carbocation. If A is not a carbon, then in this case, it's going to be an electrophile, a regular element that has a plus charge there. But B will be electron rich, so we're going to represent this by the electrons that it gained and a negative charge. If B is a carbon, then we're going to form a carb anion. When we break bonds, we form bonds. So there's a rule on how to form bonds. Two types of bond formation. Either my two electrons, they are going to combine together. So I will have two free radicals in there. They are going to combine together. And in this case, when you show the movement of two electrons, you represent this by a half arrow. Notice that there is a big difference between a half arrow and a full head arrow. So a half head arrow means that I am transferring one electron. So if you transfer one electron in both directions here so that they meet, they're going to make a sigma bond. And I can make a sigma bond by simply combining two free radicals together. I can also make a sigma bond by using the lone pair of the nucleophile and adding them to the electrophile. And in this case, I will also make a sigma bond. Let's have some examples. For the first one, you are substituting the OH with the halogen. So the first type is going to be a substitution reaction. For the second type, you are breaking the pi bond. So you have a pi bond over here, which is the double bond. You are breaking the pi bond and you are adding two sigma bonds. So you have a sigma bond here, you have a sigma bond there. This is the opposite of elimination. You're breaking the pi bond, so this is going to be an addition reaction. For the third example, you are forming an alkene and the conditions are heat conditions. So you are transitioning from a sigma bond to a pi bond in there. What you did is you broke two sigma bonds. Where are they? You broke the sigma bonds because your alkene is between those two carbons. This means that it's between those two carbons in here. So I will have a hydrogen here, okay? So I'm going to lose the first sigma bond and the second sigma bond because you cannot form a double bond, which is a pi bond here, unless you break two sigma bonds. So you are going to break those two sigma bonds in there and you are going to form a pi bond. So breaking the first sigma bond, the second sigma bond, and the pi bond that you're going to form is between those two carbons that carry the sigma bond that you broke. So you're going to end up getting your product here. This is called an elimination reaction. Elimination is always whenever your product is an alkene and it requires heat conditions in there. Over here, I'm starting with my alkene and I'm ending up with a product that has no alkene. So this means that I'm adding to the alkene so that to break the pi bond. This is going to be my pi bond that I am breaking in there. So what did I add? My addition is between this carbon over here because my alkene is between those two carbons. So my addition is on these two carbons in there. Here I have two hydrogens. And in my product now, I have three hydrogens. So you can easily see what did I add here. I added a hydrogen and I added an OH from the water. So I added a hydrogen in the water. I broke my pi bond and I added two new sigma bonds. So this is going to be an addition reaction.